In this video, we will be looking at some of the rules and guidelines for determining which orbitals have electrons in them for a given atom. Electron configurations are a shorthand method for conveying the information of where the electrons are for a given atom. As a reminder, it is the quantum mechanical theory which describes the behavior of electrons. Electrons in an atom exist in orbitals, and it is a description of the orbitals that are occupied by the electrons that we call the electron configuration. Now, the electron configuration is essentially a shorthand notation for describing the four principal quantum numbers for any given electron, and those four principal quantum numbers were initially introduced in our discussion on quantum mechanics. The electron configuration here for our hydrogen atom says 1s1. This first value here is our N quantum number. The next value that's reported here is our L quantum number. And then this final value that comes as a superscript after our L quantum number is a combination of the M sub L and the M sub S. How the orbital diagrams and electron configurations differ is that orbital diagrams, which are typically shown as a box with a sublabel of the N and the L quantum numbers, the orbital diagrams explicitly show the spin on an electron. The electron spin comes from our quantum number, M sub S. The M sub S is our spin quantum number. Spin itself is a fundamental property of all electrons. All electrons have the same amount of spin, but they differ in the orientation. The orientation of the spin on an electron is quantized, meaning they can be in one of two values. From our discussion on quantum mechanics, the values that we can use for M sub S are plus 1/2 and minus 1/2. Plus 1/2 we will call spin up, and minus 1/2 we will call spin down. In our orbital diagrams, the way that we will represent the spin up is with a half up arrow. The way that we will designate something that is spin down is with a down half arrow. So for the helium atom, the electron configuration, we would write 1s2, meaning that our principal quantum number N is 1, our L value is 0, which correlates with an s orbital, and then this 2 here is a combination of our M sub L and our M sub S. We have our M sub L value, which would be 0, which tells us that we have one orbital, which again has a value of 0 for the M sub L. The M sub S, we then have two electrons, one that is spin up and one that is spin down. And so what our electron configuration here is essentially saying is that we have our N equals 1, L equals 0, and it has two electrons in it. So it has one orbital and it has two electrons in it. In terms of our orbital diagram, it is represented in the same fashion, although each orbital is labeled with a box, and then we show the electrons as being either spin up or spin down with a half up arrow or a half down arrow. The electron's spin adds that fourth quantum number to the description of an electron. And again, it's called the spin quantum number and is given the variable M sub S. Looking at the electron spin gives us the first of our three rules or guidelines for determining how we are going to fill an orbital diagram, which is the Pauli exclusion principle. Electron spin, the M sub S value, can only have two distinct values, either a plus 1/2 or a minus 1/2. The orbital diagrams that we will be filling use a square to represent each orbital and a half arrow to represent each electron in the orbital. Each orbital will have an N value, which will be represented with a number 1, 2, 3, or 4, followed by an S, P, D, or F, which will tell us what the L value is. For how those correlate, look back on the previous video on quantum mechanics for the description of which values of L go with which different orbitals. Now, by convention, A half arrow pointing up is used to represent an electron in an orbital that is spin up, which correlates to an electron spin of a plus 1/2. If, on the other hand, we have a half arrow that is pointing down, that is used to represent an electron in an orbital that is spin down, or has an m sub s value of minus 1/2. Now, because each electron has its own unique set of 4 quantum numbers, we can't have a situation where 2 electrons in an orbital are both plus 1/2. The orbital itself is described by our first 3 quantum numbers, the n, l, and m sub l. What this tells us is that the last quantum number will tell us whether the electron is spin up or spin down, and that we can't have both electrons with the same spin. We can't have 2 electrons that are both plus 1/2, because then we would have 2 electrons that have the exact same set of 4 quantum numbers. By varying that last quantum number, the m sub s being either plus 1/2 or minus 1/2, we can have 2 electrons in the same orbital. They will share the first 3 quantum numbers, the n, l, and m sub l, but the last quantum number, the spin, will be different between the 2 electrons. One will be a plus 1/2 and one will be a minus 1/2. So each box is going to have an arrow pointing up and an arrow pointing down. It cannot have 2 arrows pointing up or 2 arrows pointing down. The spins themselves have to be paired when we have a filled orbital. This means that the 2 electrons in an orbital have to have the opposite spin. One will be in the direction of a magnetic field and one will be against the direction of a magnetic field. When we have all of our orbitals that are filled, if all the boxes are fully filled, then we will call that a diamagnetic system. To summarize, the Pauli exclusion principle says no 2 electrons in an atom can have the same set of 4 quantum numbers. Therefore, no orbital may have more than 2 electrons, and the electrons must have opposite spin when we are putting 2 electrons into the same orbital. The way we will represent that is with one of our orbital diagrams. An individual box can only hold 2 arrows, and both arrows have to be pointed in opposite directions. Now, to be clear, a box can have 1 arrow, with that arrow being either up or down, but when you start putting 2 arrows or 2 electrons in a particular orbital, one has to be up and the other one has to be down. The next thing that we need to look at is which orbitals will get electrons. When electrons are filling an atom, they try to go to the lowest energy level first. If we have only 1 electron in a system, such as a hydrogen or certain other ions in which all but 1 electron has been removed, all the sublevels, which correspond to our different L values, which are the s, p, d, f, etc. orbitals, for a given principal energy level, which would be a given n value, will all have the same energy. So for a hydrogen atom, the s, p, d, f orbitals all have the same energy because there's only 1 electron. When we have more than 1 electron, they will interact and cause splitting within these sublevels. Orbitals with the same amount of energy, which we will label as E, are said to be degenerate. So all of our p orbitals will have the same energy. So the p orbitals are all what we call degenerate. All the d orbitals for a given principal quantum number, so like the 3d orbitals, which we will talk about in a bit, are degenerate. They all have the same amount of energy. So it doesn't really matter which one of those d orbitals gets the electron first, because they are all degenerate. For multi-electron atoms, the energies in the sublevels are split. This split is caused by interactions between the charges of the electrons, shielding from inner electrons, and penetration, which is when an electron has a certain amount of probability density within another orbital. The lower the energy of the L quantum number, the less energy the sublevel will have. So the s orbitals are lower in energy than the p orbitals, which are lower in energy than the d orbitals, which are lower in energy than the f orbitals. If we look at how this works out for a standard multi-electron system, we get the following. As we increase our n principal quantum number, going from the n equals 1 to the n equals 2 to the n equals 3, 4, and 5, the energy increases. Then when we look at our L values, our L equals 0, which are the s orbitals, and the L equals 1, which are the p orbitals, we can see that as we increase that L value, the energy goes up. When we are placing electrons in an orbital, we fill the orbitals from the lowest energy to the highest. This gives us our second rule or guideline, which is the Aufbau principle. The Aufbau principle essentially says we fill from the lowest to the highest. So this means we will first put electrons in the 1s orbital, followed by the 2s, then put them into the 2p, then the 3s, the 3p, and then this is where it becomes a little bit tricky. The 3d orbitals are actually slightly higher in energy than the 4s. So in terms of filling, we fill first the 4s, then the 3d, then the 4p, then again the 4d are higher than the 5s. So we'll fill the 5s before we fill the 4d. So you have essentially two things going on here. As the n value goes up, the energy goes up. As the L value goes up, the energy goes up. And the L value of 2, which correlates to the d orbitals, the difference between that and the L equals 1, the p orbitals, is enough to put it above the next n value of 4. So the guidelines for how we will fill our orbital diagrams are as follows. The energy level and sublevels fill from the lowest energy to the highest. So we will first generally start with the 1 orbitals, then the 2, then the 3, then the 4, going s, p, d, f. Although again, keep in mind that the d orbitals from 3 are higher in energy than the 2 s orbitals. This is known as the Aufbau principle. So the Aufbau principle says that the electrons will fill from the lowest energy to the highest energy orbitals. Orbitals that are in the same sublevel have the same energy and are degenerate. What this means is that the px, py, and pz orbitals all have the same amount of energy. Our next rule is that there can be no more than 2 electrons per orbital. This is known as our Pauli exclusion principle. Again, the reason for this is that each electron needs to have its own unique set of 4 principal quantum numbers. And the last principal quantum number is the spin number, which has 2 values, m sub s being plus 1/2 or minus 1/2. The plus 1/2 is for one electron, the minus 1/2 is for the other, and because there are only 2 possible values, each orbital can only have 2 electrons. The last rule has to do with how we will fill the sublevels. When filling orbitals that have the same energy, those that are degenerate, we will place 1 electron in each orbital before completing the pairs. Part of a reason for this is that if an orbital already has an electron in it, it becomes more difficult to put a second electron in it. What we are attempting to do is to put the electron in the lowest energy orbital. So if there is one that is vacant, it will be lower in energy than an orbital that already has an electron. This last rule of half filling before we fully fill is Hund's rule. Hund's rule is put an electron in each one of the sublevels before you put a second electron in. Let's now look at a couple examples of how we would fill out an orbital diagram and then determine the electron configuration for a couple different atoms. The first one is carbon, which is located here. It has an atomic number of 6, meaning that it has 6 protons. If the carbon is neutral, then our number of electrons match our number of protons, so we have 6 electrons that we need to place. Now the diagram that's down here at the bottom is a common form of writing out our orbital diagrams. The energy in this sense increases as we go down. So the low energy is the 1s located here, and the high energy is down on the bottom right. The reason for this configuration is, depending on where you're looking, you'll see different ways of determining the relative energy of the orbitals. A common mnemonic for doing this is writing out the orbitals So 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and I'll just write the 5s here. Now, when you're trying to determine the order to fill, you do angles. So you come down in a diagonal line, then it comes back here and repeats. So you're continually filling along a diagonal line. So that would give you the 1s first, then the 2s, the 2p, the 3s, 3p, 4s, then the 3d, 4p, 5s, 4d, 5p, 6s, and so forth. So what I have here is essentially that same system drawn out in the form of boxes. We will use that to fill the electrons. So for carbon, we have 6 electrons. So we have the 1s. We can put up to 2 electrons in it. We will first half fill, then fully fill. So that's 2 electrons, 3, 4, 5, 6. So again, by default, the arrows are written as up. Our first rule, the Pauli exclusion principle, says that we can't have more than 2 electrons in a given box and that they have to be opposite in sign. Our next is the Aufbau principle, which is filling from lowest energy to highest. So we fill the 1s, then the 2s, then the 2p. And then our final one is the Hund's rule, which is half fill before you fully fill. So we have 2 orbitals that have 1 electron in them because of our Hund's rule. So the electron configuration that we would write out is essentially listing all the orbitals and how many electrons are in them. So this would be 1s, it has 2 electrons, so 1s2. Then our 2s orbital has 2 electrons in it. And then our 2p orbitals, they have a total of 2 electrons. So our electron configuration for carbon would be written out like this. Let's look at another example of zinc, which has an atomic number of 30. So if it is neutral, it has 30 electrons. So we will fill out our orbital diagram, and that will let us know what the electron configuration is. So 30 electrons, we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as I'm filling this out, you'll notice that I half fill them before I fully fill them, again because of Hund's rule. So that was 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So our electron configuration would be writing out each orbital that has an electron and then how many electrons are in that sublevel. So we'd have 1s, it has 2 electrons in it. Our 2s has 2 electrons in it. Our 2p has 2, 4, 6 electrons in it. Then we have our 3s, which has 2 electrons. Our 3p has 6 electrons. Then the next one that we filled was the 4s. So it would be 4s. That one has 2 electrons in it. And the last one is our 3d, which had 10 electrons in it. So this would be our electron configuration for zinc. Let's now look at one last example, and this is about as bad as it's going to get. Neodymium, down here. So neodymium has an atomic number of 60. So that means we have 60 electrons that we have to place. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56. Okay, and then we go to our next diagonal, which starts with the F. We were on 56, 57, 58, 59, 60. So on our electron configuration, for neodymium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then I'm going to have to continue on the next line. 5s2, 4d10, 5p6, 6s2, and then the last one is 4f4. That is about as bad as it's going to get for filling out an orbital diagram.